Okay, good afternoon, everyone. Am I audible?
Yes, sir, you're audible.
Okay. So, uh, let's go back into understanding the electrophoresis development phases. Like we discovered or we found out in last few classes that how the transition of electrophoresis actually happened from uh, uh, from a type which is referred to as free electrophoresis. And now today we will go into understanding that what is zone electrophoresis, which is basically a kind of electrophoretic procedure where you incorporate certain stabilizing media during the process of electrophoresis, and there are certain obvious advantages of incorporation of these stabilizing media for the process of electrophoresis. But before we go into discussing zone electrophoresis, let us take a short overview of what we did in the last class, and then we can move ahead in terms of understanding how zone electrophoresis or what are the advantages of zone electrophoresis over free electrophoresis, and what made it to develop as independent, uh, what you can say, method for electrophoretic separation. So we discussed about this in the last class itself, that how Tiselius moving boundary apparatus is utilized for separation of different uh, component target molecules. So if we consider that there are say there is a mixture of three different proteins that is kept in a U tube, which is the isolius moving boundary apparatus, then the concept is like you have deep or you have pure buffer, and below the pure buffer is present the mixture of protein and is again layered up with the pure buffer. So the electrodes are in direct contact with the pure buffer. And later on, when you turn on the current, then as the sample ions migrate, the leading uh, ion will be that which has essentially most amount of highest amount of charge, and mass wise it's one of the smallest molecules. So we discussed that how the situation can get complicated when we are using this kind of an apparatus in terms of understanding it, like what are the points that should be considered. So we talked about three different component molecules which are present in your sample mix. And when you carry out this moving boundary electrophoresis, then how the migration takes place and what all complications will result. First of all, there are certain challenging aspects related to separation. There is no complete separation, as we saw in the last class as well. And you can see in this picture as well as in this depiction that there is no complete separation. Like some portion of the sample molecule X here, as is shown over here, can be seen separated. However, some portion of X still remains mixed with Y. Similar is the case with some portion of Z, which seems to be separated, but some portion of it still remains mixed up with Y. And the intermediate mobility molecule, which is say Y over here, will always remain in a mixture form. Okay, so it will never get separated from X or Z protein molecule. So you will never get complete separation. So that is one point of concern. The second is the detection. How is it? How much is it challenging in terms of detection? The term, that means the method itself, is referred to as moving boundary electrophoresis because of the reason that you actually tend to find out the movement of the boundary over here. Boundary is basically made up of those sample components which are going to be moving either the fastest of all or are going to move the slowest of all. Say over here, the fastest of all is X molecule, which is obviously going to form or create a boundary which you can track. If you remember, I also told you something about the optical arrangement that is made for detection of this boundary. Is basically dependent upon interference optics, and interference optics are those which detect the change in the refractive index of the solution. So the understanding is like in the previous setup, you were having pure buffer over here. So you can place a detector device and you can place a laser over here. Okay. And as soon as there is separation, there will be creation of a boundary of X. And that boundary obviously will have a different refractive index compared to pure buffer. Okay. And that is the way in which you can judge that there is some degree of separation happening. Okay. And you don't move up the optics. You just keep it stationary at one point of time, at one position. What you can do, however, is you can place up another laser over here and a detector in order to find out whether there is a boundary formation here as well. So all in all, it's a difficult way in which you can actually detect whether the separation has taken place or not. That means this is important because you need to know when you need to turn off the apparatus, right? When you are carrying out electrophoresis, is it not essential according to you that you should know that when to stop the process? Yes. On the basis of whatever understanding we have of electrophoresis till now, do you think that this is an important point to be considered, that one should know that when the process should be stopped? According to you, is it an important point? Yes, it is indeed an important point that one has to focus upon that when should the electrophoresis procedure should be stopped. So, if the detection is so difficult, that means you can detect it only at one point. Sometimes, if you have two optical systems with you, you can detect it at 2 points, but it's a difficult arrangement to be made, right? So, the understanding is like the second important point of concern is the detection. Third important point of concern is isolation. Now, although electrophoresis later on became more or less an analytical technique, nowadays we use it as an analytical technique, or you can say molecular characterization technique for a greater or for the maximum applications of electrophoresis that we have. But when it was getting developed, it actually first developed as isolation or a purification technique or a separation technique. Okay. So, am I audible still?
Yes, sir.
Okay, good. My screen is hanging a bit, so just bear with me. As soon as this goes off, then we can move ahead. But the understanding is we were talking about the isolation aspect. Okay. So isolation itself will be a difficult or a challenging task. We discussed about this in the last class as well, that even if we get X purified from the rest of the components, Am I audible?
Yes, sir.
Okay, good. So we were talking about isolation and how difficult it could be when we are talking about, just imagine that, okay, by the virtue of faster migration of X, you have got it separated from the rest of the components. So now your purpose is to isolate X. That means you need to take out X so that you get it in pure form. That would be a difficult task again. This is because, essentially because, that as soon as you turn off the current, the sample molecules will again start to mix up together, right? And you cannot take out the sample component unless you have turned off the current. So is it not a important problem that you are going to face after the electrophoresis is done? So unless you are using it only for analytical purposes, that too is not going to be a very precise separation. But still, you will arrive at some point where you have got X separated from, say, rest of the two components. But essentially, there will be a problem that you cannot isolate X from rest of the components. And there is no, as we have already discussed, there is no complete separation. And the last point that we actually focused on in the last class itself was related to convection currents. And I'm not again going to describe how convection currents are set up, but this is basically when there is heat generation, the solvent molecules also get energized and they are set into motion. All the solvent molecules are uncharged, right? You are going to take a neutral solvent, say water, which is uncharged otherwise. But when they get energized, they are set into motion in terms that they start colliding with other solvent molecules which are not heated maximally. And that leads to setting up solvent in motion to a certain extent. And that may cause further problematic situation in terms of separation, because the solutes are being suspended in the solvent, and if solvent is set into motion, the solutes diffusion also changes. That means diffusion characters also change, and hence the sharp separation that you want will get disturbed pretty easily due to convection current. So although you are going to get some degree of separation, all these factors need to be paid attention to when you are looking at the free or moving boundary electrophoresis system. So I hope that this much is fine. Should I go ahead from this point? This, this was the portion that we already have discussed in the last class. So now we need to focus on that how we can go ahead in terms of understanding that how the situation can be different, or how the situation can be improved so that you get a better separation and all these problems get resolved. So the next kind of the electrophoretic procedure that was developed, realizing all these drawbacks of moving boundary electrophoresis, was referred to as zone electrophoresis. And the first foundations of zone electrophoresis were laid down almost in the same period when Tiselius described his moving boundary apparatus. There was another person who was working on using paper as the stabilizing media for carrying out electrophoresis. Now, you will, can anybody guess why we are calling it as a stabilizing media during electrophoresis? If we say incorporate paper during electrophoresis for carrying out electrophoresis, why we are calling paper as a stabilizing media? In certain texts, you will also see it to be referred as a supporting medium. Okay, so it is not essentially a part of electrophoresis, but it is incorporated in order to drive out certain advantages. Okay, so can anybody deliberate upon that, why we are calling it as a stabilizing or a support medium? Yes, any?
Sir, maybe
Yes.
because Maybe because convection currents could not be produced in paper and it will not lead to much more movement of solute molecules.
Yes, that is one aspect because incorporation of the basis for incorporation of the stabilizing media here is to minimize convection currents. Okay. Now, how do you feel that convection currents are going to get minimized when you add a stabilizing media? What could be the way in which convection currents are minimized? Yes, any idea? So we'll discuss upon all these aspects, why and how the convection current gets minimized when you're using a stabilizing media. Uh, uh, but one thing, okay, I am just giving you, what you can say, direction to think over it. And the direction is in terms, paper is still not a very well preferred stabilizing media, although electrophoresis, the first stabilizing media to be used for zone electrophoresis was filter paper. But we know, and we have already discussed about when we were discussing the factors affecting electrophoretic mobility. Then we discussed about that how problematic anything like paper, which has an absorbing power, can lead to, what kind of problems it can lead to. Okay. But a direct comparison can be made between zone electrophoresis and free electrophoresis if we use certain porous stabilizing media other than paper, because which are sufficiently inert, like say for example gels like agar, starch, or polyacrylamide gels. And the discussion about gel electrophoresis, although we are going to conduct it much later after we have understood the intricacies of paper electrophoresis. But the essential thing that you need to understand is that although you are incorporating a stabilizing media, the the concept that should be remembered is that the stabilizing media should be essentially inert. Okay. And we will talk about that aspect of the stabilizing media as well. But if you directly compare moving boundary electrophoretic separation as is depicted over here, as you can see, you are actually plotting refractive index against the electrophoretic mobility. So these are serum proteins which are being separated by using moving boundary electrophoresis apparatus. Okay, the same Tiselius U-tube moving boundary electrophoresis apparatus. Okay, and if you compare it with zone electrophoresis, how different it could be. Okay, as you can see over here, in zone electrophoresis, say you use one kind of a gel for separation, or even sometimes if you consider if you use paper, then you can see that every protein get or acquires a particular zone after it has got separated, or it actually gets localized in one particular area or a band, as we normally refer it as, and they are essentially well separated. There is no mix here. However, as we have seen in the last slide itself, we have seen this in the last slide itself, that when we are talking about even after the separation has happened, this area is of the molecules which are not completely separated, right? Some portion of those molecules have already migrated to different zones, but those zones are very limited. That means only the fastest moving molecule and the slowest migrating molecule are getting localized in the zones. However, here in actual zone electrophoresis, you get the molecules separated in individual bands. So is this not a very good kind of resolution that anybody can expect compared to this resolution? Now, why this resolution is not good is because under every peak, there is a mixture that is present. So if you scan the entire tube, you might get certain molecules present at a higher concentration, but under every peak, you can see this area. If you can see my cursor, this entire area is of the mixture. which is above the baseline, and the, the area under the peak actually represents the concentration of the sample. So if at all you're looking at the concentration of, say, gamma globulin, it is highly concentrated here, but you cannot say that it has separated from epsilon globulin or beta spike. Is this understood, the concept? So are you getting the clear advantage of zone electrophoresis over moving boundary electrophoresis? So in case I am interested in albumin, can I not just excise this portion of the gel and use it as pure albumin? Or if I am interested in another protein, say AAT over here, which is, if you look at, what is alpha antitrypsin. So if you are interested in alpha antitrypsin, then just you can cut out this portion of the gel and use it as alpha antitrypsin molecule, which is essentially pure, which you cannot do here. Okay, although separation you can see is not complete separation. When you try and isolate albumin from, say, globulin units, you will always get a contamination of globulin in albumin as soon as you stop the process of electrophoresis. So does it make sense to incorporate a stabilizing media to get a better separation? First of all, this is the basis of zone electrophoresis. So what do you think? Is it okay? Yes, it seems that it is going to give you an edge over moving boundary electrophoresis system, right? Then once this is understood, so it is clear enough that you are going to get a better separation. After separation also, because of the stabilizing media, the diffusion is prevented. That means sample molecules are not allowed to diffuse that readily what they can in a free solvent medium. So I hope that you know what is diffusion. Yes, anybody can anybody tell me what is diffusion? And why is it important to consider diffusion in electrophoresis? That is a more relevant question to put forth. Okay. Can anybody tell me what is diffusion? Yes. Movement of molecules from higher concentration to the lower concentration. And is it a point of concern here? Yes, solute is understood. Why is it a point of concern according to you, Bhavika? Yes. Because in electrophoresis, the major force which is acting on the molecule will be the electrophoretic or the electric field that you are applying, right? So yes. So are you referring to that means she is trying to say that it will lead to mixing of solute molecules again? But are you trying to refer it in terms that once electrophoresis is complete, or once you have completed the process of electrophoresis, then diffusion is actually a problem? Or is it like diffusion is also a problem during the process of electrophoresis? So can anybody tell that is it a problem during electrophoresis or is it a problem after the electrophoretic procedure is over? Yes. During electrophoresis, as molecules are charged, so the electric field influence will dominate. Yes, very correct. But so diffusion will not be the point of concern during electrophoresis. That's what you're trying to convey. Yes. So it's not exactly a problem during electrophoresis, but it is a problem when you stop the process, when you stop the current flow. Okay, because now the molecules are saturating, or you can consider that getting concentrated in a particular area, right? Now, if they get concentrated in one particular area, then once you turn off the current, when the current is gone, then they are free to move in both the directions, right? Because the solution here is having meager concentrations of albumin now. So now will it not prevail as the force of migration? Like albumin will try to migrate in both these directions now, because the movement of albumin will be from its region of higher concentration to its region of low concentration, right? Same is true for this AAT molecule, right? So same is true for everyone. Now, if at all you don't incorporate a stabilizing media, then diffusion will be a problem. However, when you incorporate a stabilizing media, then stabilizing media prevents diffusion for a particular period of time. That means it is not going to completely stop diffusion, but it will retard the process of diffusion to a great extent. Okay. And that is now, if you talk about gel, what's the property of gel? What do you think? What must be responsible for decreasing the process of diffusion when you're incorporating gel as the stabilizing medium? Yes. So when you use gel as the stabilizing media, the stabilization that you get is basically because of the porosity of the gel. I hope that you know this, that gels have a definite pore size. That means depending upon the concentration of the compound that you're using, say consider agar for simplicity's sake. So if I use a typical concentration of agar, then most of the pores in the set gel of agar will be of more or less similar size. So now what happens is that when it is slightly different from the concept is slightly different from uh, the concept of gels that are used during chromatography. Okay, so you cannot have the same gels that you use for chromatography used here, because in chromatography the gels that are used are in the form of gel beads. Uh, and if you know it, nowadays we get it even in the market. You might have seen this, you get certain dried gel balls, and when you put them in water, then they swell, and they attain a particular size of a bead. That is what is referred to as a gel bead. So it swells, it imbibes water, and it gets swollen, and it appears like a gel bead. Have you seen those gels which are available in the market these days? Uh, Sometimes you put them into in your fish pond or something like that. I don't know exactly what's the purpose they are sold in market, but nowadays you get them in market. You get it in dried form. They are dried, very small bead-like structures in dried form, and when you put them in water, they swell and their size increases. They become slightly bigger balls or beads of gel. So these are referred. to as the gel beads, which are used for chromatography. You don't use gels in the form of beads for electrophoresis. Okay. In electrophoresis, the gel, once you cast the gel forms a meshwork-like structure. Okay. Now, before I go any further, let me first understand that whether you have a background of understanding that what are gels in general. What are gels? Now, if you have studied something about colloidal systems, then perhaps you would be able to recall that what exactly are gels, what type of colloidal system it is. Like in colloids, you have a dispersion medium and a dispersed phase. These are the two terms that we normally use. Remember this? Yes, anyone?
So dispersed phase is solid and media is liquid. So
In
it's
gels?
semi-solid. Yes, sir.
Are you
Um,
sure about it? Dispersed phase
So
is,
dispersed phase would be liquid and
yes,
dispersion media would be solid.
yes, very correct. So, in short, what happens is that when you put anything which has a capacity to gellify, then it forms a stable media in which the dispersed phase is liquid. That means liquid is distributed amongst the solid dispersion medium. So essentially, what I'm drawing here is something like you get small pockets within a solid, what you can say, physical state of the gel. You get small pockets, and those pockets are filled up with the liquid medium. And now, because it is a colloid, you cannot work with two separate entities. That means if you separate one from the other, then both will not be stable. You cannot separate the solid from the liquid. The solid portion will dry down and will never gellify now unless you put it in contact with the liquid. Is this much fine? Should I go ahead? Yes.
Yes, sir.
Okay. So the area here, just imagine now, if you are forming a meshwork like structure when you are setting up the gel, then the area within here, this space is represented like this. So this is the space which is going to decide the pore size of the gel. So imagine this situation now. If I add extra concentration of the gelling component, then you will get such meshwork which will be extra cross-linked. So there will be extra cross-linking. And if there is an extra cross-linking, then the pore size essentially reduces. Are you getting the understanding? So if the concentration of gel is low while you are putting it for gellification, the gelling component concentration is low, like say for example agar, because you have dealt with agar previously. So if I use a low concentration of agar, then it will be more jelly-like. While if I use high concentration of agar, it will be more solid, right? And that is because there is a more intense meshwork going on there. So the pore size is the deciding factor. Now, why we were discussing all this is because imagine this situation now that your sample molecules, one molecule is of this size and the other molecule is of this size. Which molecule of these two, say suppose this molecule A and this molecule B, which of these two you suppose can pass through this pore size gel easily? A or B? Yes. According to you, which molecule, A or B, can pass through the pore size, which is given over here. This is your pore size.
B, easily.
Yes, B can easily pass through it. Okay, so which molecule, according to you, under electric field, can migrate faster through the gel of this pore size?
B can migrate faster.
Yes, B can migrate faster because it is smaller in size, right? So now the reverse is true in case of chromatography. Okay, in case of chromatography, because there is no external field applied, so the situation is like a bigger molecule can pass through the gel quite fast because it passes through the spaces in between these beads. So that's a different story altogether. Okay, but in electrophoresis, smaller the molecule, greater uh, will be its capacity to migrate through the gel, uh, depending upon the pore size of the gel. Now, why we were discussing this is because, see, B will migrate faster, so it will move a greater distance. So if I want to draw the gel like this and draw the position of A and B with respect to each other, then the situation would be, say, B, because it is migrating faster, it will form a zone over here. All B molecules will be joining this zone, and they will migrate in the form of a band. Now you will understand why I'm saying like that. While A will be retarded because it is pushed through this. Now you can argue it like A seems to be bigger in size compared to the pore size, right? Pore size of the gel. So you may argue that it will not migrate to the gel at all. But this is not a stringent pore size. Okay, the gels, as we know, are flexible enough, correct? Right? They are not rigid structures. They are flexible enough. So because A will also be dragged through, it will be facing more amount of what you can say retarding force because of smaller pore size of the gel. So it will migrate a lesser distance compared to what is migrated by B, because it is hardly going to face any problem to pass through this pore size of the gel. Is this much understood? So B will form a band like here and A will form a band like here. Is this much fine? Yes?
Yes, sir.
Okay. Now, what's the chance that once you stop electrophoretic applied field, what's the chance that B will start to diffuse away and will get mixed up with A, or A will start to diffuse away and will get mixed up with B? What's the chance? Do you believe that there is a greater chance?
There is a greater chance for B to get diffused.
Yes,
A won't
but
be.
still B need to carry a greater distance or move a greater distance, right, to get mixed up with A. Compared to A will never move, right, because it is already pushed through small pore size gel. Is this much fine? So A will be kept stationary at one point while B can start to diffuse once you stop electrophoresis. So there are methods by the way of which you can stop this process as well once the electrophoretic procedure is done. But this will take time. This is not a very fast process to happen. Am I making sense? Yes? Are you trying to get the point what I'm trying to refer? Although B can diffuse, you can use certain ways in which you can stop this diffusion later. Once electrophoresis is done, once you stop the current moving, then this movement of B can also be stopped. Now, that we'll talk about later when we discuss gel electrophoresis in greater detail. But all in all, does that sound to be a better option compared to moving boundary electrophoresis system?
Yes, sir.
Prevent diffusion? Yes, it sounds to be a better option, right? So this is one important advantage of zone electrophoresis. And that is the reason why you incorporate the stabilizing media. This essentially is, although stabilizing media does give you some degree of stabilizing capacities with respect to convection current, but apart from convection current, here a greater problem is of diffusion. And to avoid that greater problem of diffusion, you incorporate the stabilizing media. Okay, so that is one important factor. Two, because of presence of the stabilizing media, your sample molecules are essentially retarded, but your buffer ions continue to migrate freely because buffer ions are much smaller, much smaller than sample molecules. Sample molecules would be essentially macromolecules, while buffer ions, we know that they are very small in size. So essentially the current conduction will always be taking place, and there is no such situation. Okay, now let's come back to this now. There's no such problem related to greater amount of friction here. Now, why I'm saying this? Because as we just saw, that for A, there will be greater amount of friction, right? It is going to face. There will be very less amount of friction for B, but still there will be some molecules which are going to face a great amount of friction. But overall, in zone electrophoresis, if you look at it compared to moving boundary electrophoresis, there is hardly any friction. So what is different here? Why are we not considering friction as a problem? Yes. In moving boundary electrophoresis, if you look at this analogy here, in moving boundary electrophoresis, as has been shown over here, the molecules are having different charges, right? However, you can get rid of this situation pretty easily. I will come to this point and ask you this question that you should have asked to me in the last class itself. But nevertheless, I will put this question for you all. That first, let us consider this. In moving boundary electrophoresis, a greater friction is because when you start the process, the sample molecules are all mixed up together, right? It is like this, the situation. And when you carry out the process of electrophoresis, the sample molecules are moving, maybe in opposite directions to each other, right? Because of difference of their charge, those molecules which are positively charged will move towards cathode, while those molecules which are negatively charged are going to move towards anode, right? So the friction was a problem because of opposite movement or opposite drag of the molecule with respect to each other, correct?
Yes, sir.
So is it not a problem in case of zone electrophoresis? Or can you get rid of this problem right here in moving boundary electrophoresis? So that's not a point of concern at all in zone electrophoresis. Yes. Can you think about any way in which you can get rid of this problem because of extra friction that is created during moving boundary electrophoresis? Can you get rid of this problem so that it is no longer considered to be a problem in zone electrophoresis? Is the question clear?
Sir, maybe if the positive and negative electrode are not on two hands of the YouTube, and maybe within one hand. Maybe it's not a U-tube or just a straight linear. If it's a straight linear chamber.
Okay. So why do you think they must have taken YouTube as their option? And not a linear chamber? Any idea?
No, sir.
No idea. Okay. Imagine now that this is the same single tube here. It ends here. Okay, you place an anode here. How will you place pure buffer here? Did you get the question?
So how will we make the inflow of buffer pure, inflow and outlet of buffer?
So it's quite easy here because the solution, that is the mix of proteins, are going to be more denser compared to the buffer, right? Buffers, and that's what is our purpose of detection as well. When we detect refractive index, that's what you are actually going to see, correct? So what is done is that you take a vacant tube, you first fill in the tube with the protein solution, which is prepared in the same buffer that you are going to use for electrophoresis. And then you fill in the top portion of it with pure buffer. So the idea is that the protein solution being denser will not get mixed up with the buffer that easily. That means there will be diffusion, but you are not worried about it because you are going to put up electrodes and then you are going to carry out electrophoresis. Does that make sense?
Yes, sir.
Right? So can this be worked out if it is a linear tube?
No, sir.
No,
Not
it
with
cannot
that
be.
logic of buffer and
Right, right. You cannot do it, correct? So they used up the U-shaped tube. That's fine. But the problem is still not solved because the molecules are going to move in two opposite directions to two electrodes. No matter whether you use a linear tube or whether you use say by hook or crook, you are using a linear tube. Okay, technically, whatever be the problem. Say, suppose you are using a linear tube, one end is positively charged, other end is negatively charged. You somehow have placed your sample over here in between the mixture. Still, the certain molecules which are going to get attracted towards positively charged electrodes that are negatively charged molecules will move here, and some molecules will move here, right? And because it is a mixture, some molecules of positive charge may be already here, so they have a lesser distance to move. This we have already discussed in the last class. And some molecules which are already negatively charged have a lesser distance to move. That is okay. But what about a negatively charged molecule which is already here? It has to travel this much. It has to pass through the crowd of all those molecules in between. So will it not face a greater amount of friction?
yes, sir.
Right? So can you get rid of this situation? Did you not notice this, that when we were talking about the separation aspect here, then I said this, that the molecule which is having the greatest amount of charge will move faster towards one electrode, while the molecule which has least amount of charge will be held back. What I'm actually trying to refer is that all molecules are actually moving in one direction. How I can ensure this, that all molecules move in one direction? Now, this is quite easy to answer. Yes. Like it is moving towards anode, can I not say that X has 3 negative charges while the Z has only 1 negative charge and Y has 2 negative charges? Can I do this somehow? So the migration, all the molecules tend to migrate in one direction towards one electrode only. See, look at this arrangement. It has been purposefully drawn and arranged like this, so that every molecule gains a negative charge only and is made to move towards anode, so that I can place up a detector here and monitor the movement easily by using a single detection system. How can I ensure this, that this happens like this? Come on, it's quite easy. Yes. Nobody? Strange. What if I keep the pH of the buffer, say, equal to 10? This is a very large value, but still. What will happen to most of these molecules if the pH is 10? If all are proteins, what will happen to these molecules if the pH is 10? Yes? Will they not lose will all these proteins not lose their protons if the pH is 10? All their amino acid groups, will they not lose the protons when the pH is 10? So what will be the preferential charge on the protein? Yes? Come on.
It's a negative charge.
Yes. So can I not do this? Can I not ensure that every protein molecule which is migrating should migrate towards only one end of the electrophoretic cell, so that I essentially get migration only in one direction? So I'm minimizing the opposite flow of ions that can generate great amount of heat. Can I not do this?
Yes, sir.
Right? So that is got rid of. So you can adjust the pH, fine. So although, but this is happening, some molecules are still going to migrate from this end of the tube to this end of the tube. The important point to be considered here is this much amount of sample. You need this large amount of sample to be placed inside this U tube to carry out separation. And do you get proteins in terms of kilograms when you are separating? You don't get proteins in terms of kilograms, right? You get it in terms of micrograms. So, is it in any way beneficial for a biologist to separate proteins and to place them in this big tube at such a large concentration? It is not beneficial, right? And it is actually because of this concentrated protein mixture, there is great amount of friction that is created during moving boundary electrophoretic separation. That leads to increase in temperature, that leads to increase in convection current. This problem is completely resolved when you go for zone electrophoresis, because there you don't need this large amount of sample to be placed for separation. You can place it just in the form of a very small sharp band, and each individual sample components will get separated. So the amount of the sample that is required for separation will decide the extent of migration during electrophoresis, no doubt. But apart from that, it will also decide to certain extent how much amount of convection current and friction will be generated during electrophoresis procedure. So as we are almost at 2 now, I will stop here today. We will discuss about in greater details how convection currents can be reduced to a greater extent by using a stabilizing medium during electrophoresis. But I hope that this much you might have understood the basic concept that why is it